Hello. In this video, we will study depth first search method. As depth first search is one of the important uninformed search technique where the search element is uninformed and the path is also unknown. The depth first search, as the name implies, the search process gives a priority to the depth of the search space, the depth or the height or the level of the search tree or the search graph. So the height will be given the preference. A search process proceeds along a certain branch of a tree or graph till the until the last level is reached or until the leaf node is reached. And if the goal is found en route, then the search process ends. Otherwise, there will be a backtracking to the immediate parental node, and through that, going to the sibling or branch, the other branch, the parallel branch. And then again, if the search is not finding out the goal state, then again the backtracking taken place. In this way, the gradual execution of the backtracking process and the searching along a certain branch, those two things subsequently taken place to find out the goal state at the end. So we are having the depth first search algorithm and the process with an example at last. At the start of the algorithm, all vertices will be in initial state. There's an initial state and visited state. There's two states are assumed. One is initial state and another is the visited state. Each state, initial state and visited state, are represented by two arrays. So all the vertices are in initial state. And we have a stack. That stack stores the vertices after being visited. So now, at the start, all are in the initial state. Initially, the stack is empty. We will take the algorithm starts with taking the first vertex from the graph or tree. If it is a graph, a source vertex. If it is a tree, the source vertex, as well as it is referred as a root node, is taken inside the stack, is pushed into the top of the stack, in the empty stack. After that, that element is popped out from the stack and explored. Explode means generating its descendants, generating its descendant adjacent vertices. If the pop vertex is in initial state, all the vertices initially in the initial state. Now, if the pop vertex, what is popped from the stack, first we push the first vertex into the stack, then we pop. After that, if we examine and we find out the pop vertex is in the initial state, we will visit it. And the change and the state of the vertex will be changed from initial state to the visited state. And the vertex will be included in the visited array and will be deleted from the initial array. Now, what vertex, if it is in an initial state, visit it and change that state from initial to visited state. Now, after visiting, we'll explore. After visiting, we'll explore the vertex. Means the descendants will be generated. We will take the descendants or the descendant adjacent vertices and we will push all the descendant adjacent vertices into a stack. If provided the descendant adjacent vertices are not visited yet, if those are not visited yet, those are still in the initial state, then we will put into the stack. Okay. If the pop vertex is in initial state, visit it and change the state from initial to visited state. Push all unvisited vertices adjacent to pop vertex. Push means push inside the stack. All the unvisited vertices adjacent to pop vertex. So first we push into the stack, then we pop out from the stack, then we explore, means we generate all the descendant adjacent vertices of that vertex. Then we'll insert all the descendant adjacent vertices inside the stack, provided those are unvisited. Then repeat second and third step subsequently and till the stack is empty. Whenever the stack is empty, the visited array is the path by which the DFS traversal, the depth first search traversal takes place. With an example, let's elaborate the algorithm. Suppose we are having the example graph. We are having 10 vertices from 0 to 9. So all are in the visited initial array first. Initially, all vertices are in the initial array. That's the initial state. All vertices are in the initial state means all vertices are put into the initial array. And the stack initially is empty. First, we take the initial, the first vertex, the source vertex. If it is a tree, then the root node. If it is a graph, the source vertex, we will take as the initial one to be put into the top of the stack. The empty stack is filled by the first one, that is 0 here in this example. Thereafter, we are selecting 0 as the start vertex because it is a start vertex. Why we are considering this 0 as the source one? Because there is no incident edges towards 0. We can't find any incident edges towards 0 means we are not finding any incoming edges towards 0. So 0 is the source vertex, that's why. So now we are having put into the stack, then we immediately after that we pop out 0 from the stack and we'll explore. And then and there, whenever 0 is taken out of the stack, 0 is no longer the initial. 0 is becoming the visited. 0's state will be changed from initial state to the visited state. And 0 will no longer in the initial state array, but will be included in the visited state array. Then and there. Then after the next step, the 0 will be explored. Explored means the descendant adjacent vertices of 0 will be generated. What are the descendant adjacent vertices of 0 we are having? 1 and 3. So 1 and 3 will be generated. And 1 and 3 will be put into the stack in the order 3, first, 1, then. Now next one is one that will be popped out of the stack. So 1 is popped out. And in between, let's see one thing. We don't have 1 in the visited array. Only 0 is there in the visited array, visited list. 1 is not there in the visited list. So since 1 is not there in the visited list, we can visit it. For visit it, first we have to pop from the stack. Then we have to visit and then we can explore. First, we have to push into the stack. Then we can pop from the stack the topmost element. Then the topmost element, this means visited. Popping out from the stack means it is visited. And after that, it will be explored means generating the children, generating the descendant adjacent vertices. So these are the steps we are having. So since 1 is not there in the visited state till now, so 1 can be popped out comfortably and 1 can be explored. And whenever 1 is popped, that moment, the 1 will be omitted from the initial state and will be included in the visited state. So 1 will be included in the visited state array and will be excluded from the initial state array. And 1 will be explored. And the descendant adjacent nodes of 1 are 4, 5, and 2. By any order, by that order, those elements can be pushed into the stack. Those elements by any order, because this is a graph, this is not a binary tree. So by any order, those elements can be pushed into the stack one by one. So 5, 4, and 2, we pushed into the stack like this manner. 5, 4, and 2. After that, the next one to be popped out, that is the top of the stack element, that is 2. Again, the 2 will be popped out. 2 can be popped out because so far we don't have 2 visited. 2 is so far not visited. It is not in the visited list. It is very much in the initial state. So 2 can be popped out. There is no restriction on 2. So after 2 is popped out, the array is left with 4, 5, and 3, and 2 will be explored. 2 will be taken out from the initial state and will be included in the visited state. 2 will be inserted into the visited array and will be excluded from the initial array. 2 is no longer in the initial state, but in the visited state now. Now, after that, 2 will be explored and the descendant adjacents of 2 are generated like 5 and 3. 5 and 3 are the descendant adjacent vertices of 2 which are generated, and 5 and 3 subsequently will be inserted into the stack, just like this. Now the 3, the next one will be popped out. Why? Because 3 is not in the visited state so far. So 3 can be popped out from the stack and 3 can be explored further. And after exploring, the children of 3 can be inserted into the stack. The same way like the previous steps. So the 3 will be taken out from the stack because 3 is not yet visited. The stack is left with 5, 4, 5, 3. So 3 now can be taken out from the initial state and will be included in the visited state array. After that, 3 will be explored and the descendant adjacent node of 3 is only 6. So 6 will be put into the top of the stack and 6 will be in the next stage, will be popped out, and 6 is no longer visited till fourth step that 6 was not visited. So 6 can be visited now and 6 will be explored subsequently. After exploring 6, we are getting only one vertex, that is descendant adjacent of 6, that is only 9. So 9 we are having visited adjacent array of 6. So as we are having 9 as a visited adjacent array of 6, we have to include in the top of the stack, just like this. 9. 6 is taken out, and 9, the only child of 3, 6, that is put into the stack. Now the next, 9 will be taken out of the stack because the stack is not having 9 so far. 0, 1, 2, 3, 6. The stack is having, the visited list is having 0, 1, 2, 3, 6. Visited list is having so far 0, 1, 2, 3, 6. So 9 is unstacked, unvisited element. 9 is unvisited element. So 9 can be visited. 9 can be put into the stack. Okay. 9 can be popped out of the stack and 9 can be visited now. Now the 9 can be visited because we are having unvisited vertex 6. Unvisited vertex adjacent to 6 is only 9. So we will have the unvisited vertices to be pushed into the stack only, not the visited. So 9 is so long, so far unvisited. So 9 can be pushed into the top of the stack because 9 is a unvisited vertex and adjacent vertex of 6. Unvisited adjacent vertex of 6. The same way, the 9 will be popped out and the stack is left with 5, 4, 5, 3, and 9 will be included in the visited list. 9 is now visited. So we will explore 9. Exploring 9, we are having a dead end because 9 is not having any outgoing edge. So 9 is a leaf node in this graph example. So 9 doesn't have any descendant. 9 doesn't have any descendant adjacent. So no push there will be taken place. No unvisited vertices adjacent to 9 we can find, or we can find no outgoing adjacent vertex of 9 at all. So it is not pushed. The 9 will not be pushed, only visited. After that, we are having 5, 4, 5, 3. We popped out 5. After popping out 5, the array is left with, the stack, is left with 4, 5, and 3. So 5 is explored. 5 is included in the visited list, and 5 will be explored. After exploring 5, we are having the descendants 7, 8, and 6. 7, 8, and 6. 8, 7. So we are having 7, 8, and 6. But 6 is already visited. 6 is already visited. So unvisited descendant adjacent of 5. So we are having unvisited descendant adjacent of 5 is only 7 and 8, not the 6, because 6 is already visited. So actually we are having three descendants of 5, three descendant adjacent vertices of 5. When we explore 5, we get three descendant adjacents, but we will consider only those descendant adjacents which are not visited. That is 7 and 8, that will be pushed into the stack, just this way. And 5 will be put into the visited state array, taken out from the initial state. So the status of stack is 78453. 7 is popped out. The stack is left with 8453. After that, the initial state, which was 7, 8, and 4, 7, and 8, the 7 is taken out and 7 is put into the visited array. And after that, 7 will be explored. We are getting 8 only. We are getting only 8 as a descendant adjacent. So we are having only 8. That is unvisited. That is only one descendant adjacent that 7 is having. That is 8, which is also unvisited. Which is also unvisited. So 8 can be inserted into the top of the stack without a problem. So after that, same 8 will be taken out of the stack. And then we are included 8 in the visited array, leaving 4 is the only element in the initial state, and leaving 8453 at the stack. The 8 is having the descendant 9, but 9 is already visited. So 8 doesn't have any unvisited descendant adjacent. 8 is having only one descendant adjacent, that is 9. But unluckily, unfortunately, it is already visited. So it doesn't have any unvisited descendant adjacent vertex. So no push. There is no unvisited vertices adjacent to 8. That's why no further push into the stack. So we will start with the next step, with the stack having the elements 8, 4, 5, 3. So 8 is taken out of the stack. 8 is again explored. We are getting 9. 9 is already visited. 9 is already visited. So there is no push. There is no, 9 is already visited. So we will not. Now 8 is popped up. Now 8 is popped out. Whenever 8 is popped out, 8 is not visited. So 8 is popped out, no problem. So whenever 8 is popped out, it will be visited. It will be included in the visited array. And we will be finding all the descendant adjacents of 8 which are not visited. Only one descendant adjacent of 8 we can find, and that is 9. But unfortunately, it is visited. So there is no descendant adjacent of 8 we can find. So no push. The stack is having 4, 5, and 3. So 4 is popped out. 4 is 4 was there in the initial state so far. Now 4 will be included in the visited array. And 4 will be explored. After exploring 4, we are getting only 7. 7 is visited or not visited. 7 is already visited. So we will not push 7 inside the stack. There is no unvisited vertices adjacent to 4. 4 is having only one descendant adjacent, that is 7. Unfortunately, that is visited already. So 4 is not having any unvisited adjacent vertex. So 7 will not be inserted into the stack. So after that, the stack is having 5 and 3. Only the stack is having 5 and 3. So after the next step, so we are having the stack as 5 and 3. So the 5 will be taken out in the next step for exploration. If the 5 will be taken out, we are having 8 and 6, two descendants. But 8 and 6 already visited. 8 is visited and 6 is visited already. So there is no unvisited descendant of 5 we can find. No unvisited descendant vertex. None unvisited descendant adjacent of 5 we can find, because 5 is the next one to be explored. So what we have, we are living with 3 in the array. So 3 is popped out. 3 is already in the visited state. 3 is not in the visited state. Okay. 3 is already in the visited state. 3 we have already visited. So all unvisited vertices adjacent to pod vertex. What are the adjacent vertices of 3? That is 6. Descendant adjacent only 6. 6 is also visited. So there is no more push. 3 is already in the visited state. 3 is popped out. 3 is already in the visited state. All unvisited vertices adjacent to pop vertex. That is, no unvisited vertices adjacent to 3. So no push. The stack will be empty. So the path of DFS traversal from the starting node to the goal node. When the starting node is 0, the goal node is 9. The source vertex is 0. The lift vertex, the last goal vertex is 9. So we are having this path 0 to 1, 1 to 2, 0 to 1, 1 to 2, 2 to 3, 3 to 6, 6 to 9. Okay. Now 9 to backtracking to 5 again. 9 to 5, 5 to again 7, 7, then 7 to 8, and 8 to backtracking 4. We can have the backtracking to 4. Okay, by anywhere. So we are having this is a traversal of this particular graph. This is a traversal of this particular graph. So what we have, this is a traversal, DFS traversal of the graph. So this is the DFS traversal that containing the visited nodes, the nodes visited in the order. First 0 will be visited, then 1, then 2, then 3, then 6, then 9, then 5, 7, 8, 4. So this is a DFS traversal. We don't know what is the goal state actually. Even 9 is not explicitly mentioned as goal. 9 is having, 9 is a leaf node. 9 doesn't have any the outgoing incident edge. 9 is not having any descendant adjacent. But that doesn't mean the 9 is the goal. So we are not knowing the goal. So this is a DFS traversal of this particular example. Because it is an uninformed search. So we have this particular traversal. This is a traversal. We have. We have this a traversal. So this traversal will follow this traversal in this particular example, according to DFS. Now, a program will elaborate the program with an example of a maze. A maze is an array. This program is actually built on the platform of a maze. A maze means it is an array. It's a two-dimensional array or matrix type element that is having some rows and columns. All values are binary, 0 and 1. 0 means the path is clear, the process can move, the search process can move through 0. And 1 means a wall, the search process will stop here and will backtrack. So this is a maze platform on which the search will take place. Now we are having this particular search, DFS function. We are having maze, start and goal. And we normal usual declarations and initializations will have. Then in the goal state, if a certain XY assignment, X means the value of X axis, Y means the value in the Y axis. So in the matrix, 0, 0 means 0th row, 0th column. X represents row count, Y represents column count. When for a certain row and column combination gives you the goal state, you stop. You return the path. Otherwise, if it is not the goal state, then if the row counter, the row index, the row counter lies between 0 to row number 1, total number of rows minus 1, and Y, the column counter that stays between 0 to column minus 1, cols minus 1, 0 to total number of columns minus 1. If X and Y is confined within the range of 0 to total number of rows minus 1 and 0 to total number of columns minus 1, and maze XY for certain row and column combination, the maze entry is having 0. 0 binary, this means there's a clear path and XY not in visited. XY means either the row count or the column count. This XY is not in the visited array. Then we will include the XY in the visited list. We'll include the XY in the visited list if it is not already in the visited list. Dx and dy are the change in X and change in Y. So dx is defined as the first parameter, the dy is defined as the second parameter. There are 4 options. 1, 0 means the X proceeds 1 step further and the Y remains fixed. Minus 1, 0. X goes backward, is the backtracking. XY axis, backtracking along X axis. It is a horizontal backtracking. The X axis, the backtracking along X axis, where the Y axis value is fixed. So we are having, there is no movement of Y axis. So it's a vertical backtracking. 0, 1 means the Y will proceed one step further and X will remain as it is. So it is going down. 0, minus 1. The Y parameter goes minus 1 means it is Y along the Y axis, it is going one step back, while the X axis element remain as it is. So it is a backtracking along Y axis, it is a backtracking along X axis, it is a front movement, forward movement along X axis, it is a backward movement along, is a forward movement along Y axis. 1, 0 forward movement of Y X axis, keeping Y axis value constant. Means the row increases by 1, column fixed. Minus 1, 0. Row decreases by 1, column fixed. Means the first that row vector that decreases by 1 and the column vector remains fixed. The 0, 1 means the row vector remains fixed. The column vector increases by 1. So going to the next column. 0, minus 1 means the row vector remains fixed. The column vector backwards goes backward one step back. So this is the way the movements can be represented. Either it rows increases, column remains fixed, or row decrements, the column remains fixed, or the column increases, row remains fixed, or the column decreases, the row remains fixed. The row-wise movement is dx. The column-wise movement is dy. The columnar movement means dy. Okay. So whatever movement we are having, all these four, it is a subset of all these four combinations. Whatever movements we are having, like dx and dy, change in x and change in y, is the subset of all these combinations. Now, next is means x plus change in x. Dx can be negative, dx can be positive, dx can be 0. Dx can be plus 1, dx can be minus 1, or dx can be 0. 0 means there is no movement. Minus 1 means the row decreases minus 1. Row decrement, row count decremented minus 1 means backtracking to the previous row. And x plus 1 means going forward in the next row. And dy is negative means going backward in the previous column. Dy 0 means staying in the same column. Dy positive means going to the next column. So we are having the next value of x and y. The xy dimension of the next element is the current x plus dx and current y plus dy. So we are having this condition. If next x confined within the 0 to the total row count, and next y confined within the range of 0 to column count, and next x, next y not in the combination, not in the visited list, then we should visit it. And we should insert that thing, that new x and new y into the stack, and the path will be incremented by extended by incorporating this new x and new y. So this is the way we are creating the path from source to destination, where the starting node is referred as 0, 0, where the starting node here is given as a parameter 0, 0. It starts with 0, 0, 0th row, 0th column. The goal node is referred as fourth row and fourth column. So basically the start starts with the 0th row, 0th column. This 0th row, 0th column means this 0, particular this entry, and fourth row and fourth column means this entry. From this to this, the traversal will be made. How the DFS traversal is made? See the output. From 0, 0, we are going to 1, 0. 0, 0 to 1, 0, then 2, 0, then 3, 0, then we can't be 0, 0, 1, 0, then we are having 1, 1, sorry, then we are having 1, 1, then 2, 1, it can't be 3, 1. From 0, 0, it has the traversal to 1, 0, 1th row, 0th column, then 1th row, 2th, 1th column, 1, 1, then we are having 1, 2, but it can't be 1, 3 because there is a 1. One is defined as a wall. One is not in this condition. Maze xy is 0, then only we can proceed. The movement is allowed. If maze xy is 1, the movement is not allowed. So it will have a thrush over here. It will have an obstruction, okay, over here. It can't go through this path. So it will backtrack. So it will back to the 0, 2, 0, 1, 2, 0th row, 2th column. So 0, 2. The next one is 0, 2. Then 0, 3, no obstruction. Then 0, 3. Then 0, 4. Then 1, 4, 2, 4, 3, 4, 4, 4. In this way, straight it will go. So the backtracking is taken place like this. Then it will backtrack. Then it will go just like this. So the DFS traversal order, according to the order of traversal, the output has come. That shows the order of traversal from the source node to the goal node. Thank you. This is all the DFS algorithm and the program and by which the DFS works. Thank you so much.